All right. So last time we basically talked about the motivating problem for the state pattern. Let's just recap what we have done last time. I'll present again the motivating problem for this design pattern here, and then I'll give you the two best solutions, and I'll repeat the criticism again. It's really important to understand why things are bad before you learn something good. And then we'll go directly to the state pattern. So go about the abstract idea, architecture, and also the Eiffel code. Okay, that's what we'll do. Okay, so now let's go to the slides over here. Let's start from the very beginning. So what's the kind of problem we are trying to solve? Whenever you're trying to learn a new design pattern, think about what's the context in which you can apply this particular pattern. It's not a silver bullet, so it's only applicable to certain contexts. So every time if you want to deal with any interactive system, for example, this is one simple flight booking system over there. So I emphasize the word interactive, which means the system should really keep getting the user's input and somehow internally make a transition to other states, like different web pages. So that's kind of the nature of the system. So what we will do is we'll try to see every time you're given such problem there, abstractly speaking, how should the solution look like? Abstractly speaking, this is something you should come up with, which is a state transition diagram that many of you should learn about finite, deterministic finite automata back in 2001. If you haven't, don't worry. Basically, it's basically drawing circles and arrows around. Okay. So now let me just review this very quickly. Okay. So that's what we talk about. We got finite state machine over here. That's what we have. And also, for example, let's say over here, we have a state called sit inquiry over here. And over there, we got two outgoing transitions. One of them is we can either go out by making transition number 2, in which case we'll go to state number 2 for flight inquiry, right? It's state dependence. And you can definitely find a corresponding entry in the transition table. For example, how can we find this particular transition? You can see over here, the way we present a transition table, quite obviously, it can be implemented by a two-dimensional array, right? You got the row and the column. And what about the rows over here? The rows correspond to all the states you're in. In this case, we got 1, 2, 3, 4, 5, 6. 6 states. That means we got 6 rows over here. What about columns? Columns over here represent how many possible choices the user might make to say, I want to go to another state. In this case, we got 1, 2, or 3, right? So now, let's say in the case of state number 3. State number 3 is over here. So we should look at row number 3 over here for the transition table. And then how many choices do we have? Apparently, choice number 1 is not applicable. That means you simply got not applicable over here. So it will just be empty. On the other hand, you can either go for transition number 2, in which case you will go to the target state number 2, which is over here, right? That's how you look up the transition table. Any question about how you can relate between the finite state machine to the transition table? We actually need that for the solution, for the state pattern. It's the most critical bit, abstractly speaking. Of course, how to come up with the state diagram is kind of beyond the scope of this course. It will be up to your judgment. What will be the appropriate state to make, and what will be the appropriate transitions to make. Okay? Okay. After this, we talk about different solutions. Let me just remind you very quickly. So the main design challenges is whenever you got n number of states being n, theoretically speaking, you can have a very dense diagram, in which case it can be up to n squared. It can be quadratic on the number of states. So that's why we deserve a very good pattern to really handle this. Okay. Okay. So this we have already covered last time. What I'd like to show you very quickly is the two bad solutions very quickly. So the very first solution that we did basically goes like this, very straightforward. Whatever control structure you have over here, abstractly speaking, you reflect that directly into the entire system like this. So how do we do that? For example, you can see over here we have state number 3, which can go either by transition number 2 or go by transition number 3. To declare for each state, we simply have a label over here. Like what you learned in 2021, you have label and you can go to a particular label. And then for state number 3 particularly, we can eventually say, once we get users' request to either go by transition number 2 or go by transition number 3, then we'll just go to other states directly, right? For example, if you are in state number 3 and you are taking option number 2, you will go to state number 2 again. So that means we'll go to this particular states and then try to execute the code over here, right? So that's kind of the idea for the first solution. Not only that, you can see that what goes before checking the user's answer, we have to go for like a loop over here. Basically, we'll let the user keep trying to enter some answer or some choice until all the answers and choices are valid. If they are not valid, we just let them retry rather than crashing the program, basically. Okay? You can. It's a very general pattern over here. Okay? But you can go through the detail. I will remind you very quickly about the bad thing, the disadvantages for this solution here. Okay? Number one, we simply use labels and go to. We suffer from the so-called spaghetti code for your design. Because at the runtime, you simply can go from, let's say, for example, one label to another, and then from that to another. So that it would be very difficult for you to trace the runtime behavior for your system. That's number one. And number two, because somehow you have no separation of concern. We talk about this control structure over here, but it is directly hard-coded as the entirety of your system over here. So that means every time if I want to make a change to certain states or certain transition, that's going to affect the system directly, entirely. Okay, that's the second thing. And the third thing, which is the worst, this solution here is not reusable because since we hard-coded the entire state transition diagram, which is only specific to the reservation system we saw in the first slides, we cannot directly apply this solution to other problems. Let's say today, if I change that to maybe some system like Amazon, to buy some goods rather than flight reservation, I cannot reuse this solution right away. Okay, so that's kind of the bad thing about the first solution. Okay, hopefully you wouldn't go for the first one. The second solution that we talk about is trying to improve the first one a little bit. So remember I talked about separation of concern. Basically, we want to make the control structure as a separate feature only in your class. And other features might be responsible for other things, but it's only the one single feature that is going to be responsible for the transition table. Okay? For example, you can see that in the second solution, what we are trying to do here is we declare a feature called transition. Okay? I just remind you very quickly, we did some exercise together last time. So now we simply, the feature is going to take 3 inputs. It's going to take what's the source states. We simply represent each state by integer, right? From 1 to 6. And also, what's the state you want to move from, and what's the choice that you want to take, right? So now, for example, if we call transition feature over here, and then we say the current state is simply 3, and we want to make a transition number 2, then what should be the target states, basically, right? How do we know that? Well, you can either look up the transition table or to look at the original graph that we have over here. Let's look at the transition table. For this particular call to the transition, the source states is simply 3. That means we should look at this particular row. And then the choice that we want to make in order to go out is number 2. So that means we look at this particular column. Look at the intersection, we know that this is the target states, right? Basically, if you are in state number 3, you're making a transition label as 2, you go to state number 2. Okay? So 2 is the return value over here. So it's going to return 2. Okay? And you can do the similar exercise for the next one. So let's not repeat. Okay. And of course, you can easily just implement the transition table using a two-dimensional array, like an adjacency matrix strategy that you learned from 2011. Okay? Now, given that we got this transition feature over here, let's see how we can elaborate on the details for the second solution. The second solution actually is not too bad. For any language that does not support object orientation, it would be a very obvious choice to go for. But we're going to see what it will suffer from for the non-OO solution. And then we'll see, since we are using object orientation, which can let you design a big system. So we'll go for OO, which is a state descent pattern. But let's criticize on this not OO solution. Okay, let's go over the idea very quickly. So the idea really is, so people, if you look at a textbook, you can even call it top-down design or hierarchical design because we've got different levels. Okay, let's see. So at the top level, you simply going to define how you are going to interact with the user, execute session, right? Basically, you're gonna say, I'm gonna run a loop as long as the user has entered some invalid choice or invalid answer. I'm gonna let them keep trying until they enter some valid answers or and choices. And then after I have got the valid choices and answer, I'm gonna process that accordingly, depending on what the current state is. So for execute section there, it's going to be divided into different stages. That's why we got another level, level 2. Okay, just level 3, level 2, level 1. For level 2, we're gonna initialize the states and then make some transition, and then we're gonna execute according to what the current state is. And then we're gonna check to see if the state is already the final state. For example, the user has already paid for the current reservation. That means they're done. They can simply log out, and we are done for the current interaction. Even further, for this particular execute states, which we'll see in more detail, the execute states feature or stage over here, we're going to subdivide that into different stages. How do we execute a particular states? We are going to first of all display the state specific information to say now in this stage, because you want to in this state you want to reserve a flight, so you want to enter your credit card number, for example, okay? And then you're going to read some input from the user, for example, credit card number. And then you're going to verify to see if the credit card number is valid. And then you're going to give some message to the user if either they have entered a valid credit card number or not valid credit card number. And then eventually you can just do some processing, maybe charge them, for example, right? Okay, any questions about the high-level design for the second one? It's hierarchical, no OO, okay? Not really. We're not, even though we're using IFO to implement, but we are not really exploiting the OO features fully. That's why we need a state design pattern, okay? I'll highlight the insight very soon to see how we can go from the second poor design into the good design. That's really the insight you want to pay attention to right away. Okay, let's elaborate each one of them. I'm gonna first tell you how to implement this execute session here, for which you will see initial, transition, execute state, and its final. And then we're gonna see exactly how you're gonna implement for the execute states. Let's get a feel. And then we'll start criticizing about this design, which we haven't done fully back from Tuesday. Okay? Let's now see the detail for execute session. Let's see how it looks like. Now for execute session over here, as I said before, you're going to have different stages. For example, you're going to have something called initial, okay? And then you're going to say until the current state is actually final. So what's the current state? Current state is simply just a local variable that we are keeping track of between 1 and 6. It can be between 1 and also 6 because we got 6 different states for this particular application, okay? Just integer type, okay? And then every time when we are doing something over here, we simply say, whatever we're going to execute the current states over here, and then according to the current states. And then the current state is going to be changed based on whatever transition we have to make, right? So here, this transition here is the feature we just introduced, right? For this second solution, it's a feature, like a transition table. You can see that the advantage for the second design compared with the first one is whenever you want to look up which transition I should really make, I can simply call this feature. The feature is dedicated for this purpose. Whereas in the first design, it's actually scattered out using the go-to and label. Okay? That's kind of the advantage. One thing to note. You can see that over here, I want you to pay attention to this one specifically. If you look at what we are passing over here, current states, right? Current state is passing to execute states, and execute state is over here. That means when we go from level 3 to level 2, we are passing certain information over here, right? Which is the current states. We are passing something, okay? Okay, one thing to note. And then we'll see why it could be a disadvantage in just a moment. Any questions until now? Okay, let's see even further. I would like to show you how we are, given that we're going to pass the current states to execute states, let's see how the execute state is going to be defined in details. Okay, let's go to the next one. So now we talk about execute states over here, okay, at the second level. So we already moved from the top level to the middle level. Execute state basically is going to be divided into, again, display, read, correct, message, and process. Okay? Let's see that very quickly. Again, you can see that the input we have to take is the current state of type integer from level number 3. And then you can see that we're still running a loop to say we're going to keep reading from the user until they enter something. Okay? So that's valid. So what do we have? We have, I'm going to highlight in different color for you, and then I want you to notice one thing. We have display. We have read the answer from the user, read the choice from the user, like what next state you want to go to. And also whether or not the answer is correct or not. And also print some message to the user. And also eventually, once the user enters something that's valid, we're going to process. One thing to note, which I also highlight over here, you can see in order to do all the features I have just highlighted, there's one piece of information that's required, which is the current states. For example, if I want to display over here, if I want to display certain information for some particular states, I need to know what state I'm talking about, right? If the state is for inquiring the flight, I need to display something different. If I want to display the information for maybe confirmation stage, maybe the message will be different as well. So the current state information is the context. Okay. But can you see any disadvantage over here? Or at least some repetition over here? Well, not really repetition, but it seems like it's so inconvenient. Every time we want to do something over here, we have to pass the current states. We have to pass the current state here, 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 and here. That's not very convenient. Eventually, what we want to really have is to somehow make the current state concept into a separate class. That's what the essence for the state pattern is about. Now, I'll give you a very quick review. I want to just copy one of the lines over here. When I say display current states, okay, before I talk about how to move on to the third solution, the state pattern, before I show you the code, how do you think I should really, roughly speaking, how do I implement the display feature? You can see from the signature here that the display feature is going to take one single input, right? Which is the current states, which is an integer. And the range can be from 1 to 6, right? Can you just think about what would be the control structure for this display implementation? What would it be, roughly speaking? Okay, you're talking about the precondition, right? So maybe display should have a precondition saying the current state you're passing should be between 1 and 6. I agree. What about the implementation part?
Just a system of
but what should you print? Because you might be in state number 1, or you might be in state number 3. Depending on which state you are in, you might have to print something out. You might print something different, right? So what would be the required control structure for you to print out state-specific information? Go ahead. Okay, can you make it a little bit even more specific? You're right on right track.
Current state equals 1. Else if current state equals 2.
Yeah, exactly. Thank you. Thank you. So
I have to write that for a display, and then again for read answer, and then again for read choice.
yeah, I agree.
Copy your if else again.
Yeah.
And what you're going to say next is that whenever you add a new state, you have to write another if else, and all of these come 6 functions.
Apparently, we got someone who did a pre-study, which is good. All right.
Switch cases are way easier to read.
Huh?
Switch cases are way easier to read.
Well, you either use the switch case, or if then else is a syntax issue. But conceptually, you still have to see which state you are in, right? Depending on what the value is. All right? Okay? So now, basically, over here for display, you have to somehow do some discrimination on what the value is for the current states. If it is 1, I do one thing. If it is 2, I do something else. If it is 3, I do yet something else. Okay? That's one thing. Okay? Let's have a look on that. Okay, let's have the slides over here. I want to show you, and then we can see why it would be bad. Okay, That's the execute session we just talked about. And then we got execute states, which we just said. And now let's look at display specifically, okay, for display. Oh, by the way, you can see that for all the feature we are calling, we have to pass a current state. That's one thing, okay? That's something to note for all of them. And then we want to see how similar it would be for each one of them. For example, how similar would the code for display look like the code for read answer? How similar would it be? Well, as we agree, for every feature over here in the table at the first level, we have to somehow discriminate on what the value it is for the current states and do something accordingly, right? So let's see exactly how we're going to do for display. So now, as you said before, we're going to have a require for the precondition. It should be between 1 and 6. But in reality, it can be between 1 and 100 if you got 100 states, right? But now, how do we know which one is which? Of course, we need some if statement here. If the current state is 1, then we display for this particular state. If it is current state is 2, then we do another thing, right? And etc. Are we okay so far for the display? Okay, so now here, this poses two challenges for us, okay? First of all, is this control structure going to be duplicated somewhere? Well, if you say yes, where, for example? Which feature? Well, basically, for all the feature that has the current state as the input, right? How many such features do we have? Well, if you go according to the table over here, all the features at the first level has to repeat such structure. Agree? And we are only talking about a very small system where in the first level there are only about 5 or 6 features. In a realistic system, you might have 100 different features to handle at the first level, in which case you gotta repeat the control structure for 100 times. What do you mean streamline to? Maybe you're asking about how we can improve this design. Yes, that's exactly what we're talking about. Let's first of all appreciate why it is bad, and then we'll try to see how we can. Yeah. Okay. We know that repeating the same if structure, if then else structure according to each state is bad. Okay, repeating that's really bad. And also, what's even worse? Okay. Again, remember we talked about single choice principle. Okay. Again, anybody can summarize what single choice principle is for me, even though it's not covered in the midterm. Single choice principle. Yes, go ahead.
Changing a code doesn't require you to change in
the multiple.
At most you could change your code once without changing other places where the code is kind of
Yeah.
used.
Yeah. Basically, whenever you want to introduce a change or make a fix to your system, there should be just a minimum number of places you should really fix. Typically, just one. That's why it's called single choice principle. Now, in this case, can you imagine how it is going to violate the single choice principle? Let me just give you a hint. If you look at the structure for one of the feature, which looks like this, display. Okay? And we know that this if then else structure is going to be duplicated for all the other feature, like a process, message, validates, etc. Right? How is that going to violate the single choice principle? What kind of change can you introduce so that it's going to violate the single choice principle? Adding a new state, that's good direction. What happens if I want to add a new state? For example, abstractly speaking, let's say, let me just go to the iPad and show you exactly what I meant. Let's go back to this original transition diagram over here. Conceptually, if I want to add just one more state over here, let's call it state number 7. Okay? And as state number 7 over here, let's just say state number 7. And state number 7 might go here, and then, or you go like this, for example. Okay? Now, if I try to introduce this new state, how would I have to modify the display feature, for example? Just adding one state. Yeah, that means my discrimination at the moment is not exhaustive, right? I need to add just one more check for the case to say, else if current state equals 7, then I need to do something. Exactly. That's why it violates the single choice principle. That's why this design is bad, right? So, I'm not saying this design is very good. It's not ideal, but it's kind of better than this first one. But we want to really get to the as good solution as possible. So now, again, how does this design over here violate the single choice principle? Whenever you want to think about how it violates the single choice principle, think about what kind of change or extension you can introduce to your system. In this case, I simply make one example to say, I have introduced a new state, number 7 over here. That's all I do. I make a change to my requirements. And the consequence of that is I need to add, not just for display, but for every other feature that would take the current states as the arguments. I need to add an else if to say else if current state equals 7, I need to do something accordingly, right? So that's definitely multiple places I need to change. So that violates the single choice principle. Okay? So now, are we okay with this? Now let's see exactly the insight to see how we can move from this poor design into the good design, which is state pattern, by exploiting OO, object orientation. Let me give you a little bit hints, like a warm-up. Remember when we talk about polymorphism and dynamic binding, okay? If I can somehow have a type called states, like a class called states, and then polymorphism allows me to introduce as many descending classes as I want for the state class, so that at the runtime, I can have different dynamic types for this particular static type, right? Okay, good. That's about polymorphism. And then, let me go back to the slide, iPad to show you what I want to show. I want to do some comparison over here. Okay, if I look at this one here, we know that from the poor design over here, if you say display and take the current state, we got to do lots of discrimination if then else, right? Now, the ideal solution would be if I can say something like this. I'll write it down in red. If I can somehow say current states rather than of type integer, so in this case it's integer for the poor design. If I can make it a type, maybe just called states, for example. If I can, let's imagine we do have a type called states. And then rather than having this as the context input, why don't we make it a context objects? We keep talking about context object, right, for object orientation. The very essence about object-oriented design is, depending on what the context object is, you're going to do things differently, even though you're calling the same feature or method. For example, let's say this. If I say current states dot display, you can see we're basically talking about the same information in here, but I'm just swapping the order, but really swapping the paradigm that we are thinking. In this design over here, it's not OO. We're just passing whatever the context information around whenever we need it. But in this second design, the third one, the state pattern here, which we're going to show you the detail, we're basically making the notion of states over here a context objects. And now, at the runtime, what kind of mechanism ensure us that display the right version will be called? Because we know that because of polymorphism, the dynamic type for current state can be confirmation, it can be flight inquiry, it can be maybe seat inquiry, and etc. We got 6 possible dynamic types. What kind of mechanism ensure the right version of display will be called? Dynamic binding, exactly. And now, does dynamic binding require you to say anything like, if as instance of seat inquiry, I need to call this version. Else if as instance of confirmation, I call another version of display. You don't have to, right? You simply say current state.display. And all the if then else, this kind of checking is done automatically for you implicitly by the runtime because of dynamic binding. So guys, that's the very essence about moving to the second design to the third one. Rather than using explicit parameter over there, current state being integer, we are making use of polymorphism and dynamic binding that's supported by OOP. Okay? Are we okay? Of course, I'm only talking over here, but we're going to see details in just a moment. But if you understand so far, it's a good sign. Good. Okay, now that's about the display, and then we are moving very quickly to the end of the, okay, so now you can see that for the poor design, you're basically passing the context information about states from level 3 to level 2, and then from level 2 to level 1. Okay, that's not good. Okay, if you're finding that you're passing something way so often as parameter for the feature, you better make it a separate class or as the context objects. That's the point. Okay. Again, the most important comparison to have in your mind is we are moving from having a context input over here and change that to the context objects. Okay, that's really the change we are making to move on to state design pattern. Okay, after this, let's see what we can do. If you look at the textbook, there's something called law of inversion, but that's exactly what I'm trying to say. Let me just read it out and let's see. If your routines or your feature exchange too many data, for example, current state being the integer, right, as the input, then put your routines in your data. Simply means we're going to create a new class for the notion of states. So what we're going to do is we are simply going to say we're going to factor out all the notion about states as the input over here into a separate class. That's what we're going to do. That's how we move on from this poor design into the final solution for the state pattern. Okay, that's what we're going to do. Okay, and then let's see what else to say. So we have to modularize the notion about states into a class called states. That's what we'll do. And then we have to encapsulate, basically going to hide all the necessary information or encapsulate, put them into the class states. And we'll see exactly how we can define that. Okay. Okay. So now, this is kind of the conceptual view that we're going to have. So let me just show you over here the comparison. Okay. Again, let me just repeat very quickly. So now this is the poor design. Okay, and this is the good design. How about that? The poor and good. Okay, the poor design simply pass around the state information between levels. But now for the good design, basically we're going to basically put everything that's related to the states into a single class. That's what we're going to do. Okay, conceptually. Okay, now in the poor design, the current states is represented as an integer. Just integer, not the primitive type, basically. And then when we say execute the session, we simply say pass the current state around as an integer. But now in the OO design for the state pattern, we're gonna declare current state being of a type states. That's what we're gonna do. And then when we say current states dot execute session, first of all, we have to make sure. How do we make sure this second line of code over here? If you look at this line of code, how can we be sure that this line will compile? Well, we have to make sure execute session is declared in the class called states, first of all, right? And how can we be sure that at the runtime it's going to execute the right version? We have to make sure we redefine the execute session in each class accordingly and let the dynamic binding to do its job automatically, which we don't have to worry about. And there'll be no if then else statements, which will violate the single choice principle in the state pattern. Okay. All right. So now let's have a look. I will first go over the architecture using bond diagram to show you how the state pattern will work. Let's go over the architecture first, and then I'll give you just a few examples quickly. And then we're going to see the code to see how you can define the states and also how you can define all the application altogether. Let's see. What we will do is, first of all, so let's talk about architecture. So there's a bond diagram over here. So there's a bond diagram. Okay. You can see that we have the application over here. That's the clients. And we do have a client-supplier relation over here. And the supplier is the states. So what does star mean over here? Defer, right? Defer, good. Yeah, defer means the state class itself contains certain features that have not been implemented, like an abstract class in Java, okay? And then we're saying that the defer class called states has a list of descendant classes, okay? And each one of them is, what does plus mean, if you remember? Implemented or effective, right? Implemented is fine. Effective is just more Eiffel term. Okay, so here we got 1, 2, 3, 4, 5, 6, and 7. Okay, final state as well, depending on how many states you have. So now you can imagine that. Oh, one more thing to mention At the state class level over here, let's see what we have. We have several deferred features over here, which means these features are not implemented at the state level. They will be implemented at the different descending classes. We got read, we got display, we got correct, we got process, we got message. Okay. However, you might be wondering, there's one single feature in the state class that's plus. Okay, I want to highlight that for you, which is called execute. Okay, basically, this execute feature being with a plus, that means it's already fully implemented at the state class level, at the deferred class level. So that's going to be another design pattern I want to show you, which is called template pattern. Very quickly, the execute feature is going to somehow show you the way you put the read, display, correct, process, and message all together in some certain control structure. It's more like a template. And then at the runtime, when you try to call execute, okay, let me show you. I will just say that very quickly because I also want to show you the code in just a moment. Let's say this. Over here, if I have S over here of static type state, okay? And then I can try to make this particular creation feature over here. That means I'm changing the dynamic type of S into sit inquiry. Agree? Okay? And then when I can also try to call S.execute. Okay? This will compile because execute over here is defined at the state level. So that's fine. And I can also change the dynamic type for S into confirmation. Okay? And then after that, I can simply call, again, the same line over here. Now, if you compare these two lines over here, the two blue lines over here, are they going to call the same version of execute? You know what? This is a bit tricky. How about this? Let's look at, okay, this one is really important, okay? So you can see, I haven't shown you any code yet, but just from the design diagram, we can already see many insight into the pattern, okay? Let me just say this. Over here, let me say here. S.execute, let me call that number 1. S.execute, let's call that number 2. For number 1, which version, okay, the version of the execute that's going to be called in line number 1, where is that defined? In the states? Let me repeat the question, you can see from the diagram. If I look at the line number 1, S.execute, my question is, where is that execute feature that's going to be called at the runtime defined? In the state, right? Because if I look at that over here, execute over here is simply with a plus. That means fully implemented. So there's only one single version. If I wanted to show that execute was redefined, I would have shown plus plus somewhere in the descending classes, right? But here, there's no. There's only one single version of the execute, okay? Now, how many versions are there for read, display, correct, process, and message? How many versions? How do you know it's 4? Are you sure it's only 4? 7, right? Depending on how many descending classes you have, it is. Right, so over here, you can see execute is only one version. That's in the states. On the other hand, these features over here that's already deferred at the state level, they will become effective at all the descending classes. 1, 2, 3, 4, 5, 6, 7. 7 versions. Okay? Let me say one more thing. Okay? And then also, for line number 2 over here, we know that it's also going to call the same version of the execute that's defined in the states, right? Now, let's go a little bit further. How is the execute going to be defined? Let me give you a very, very vague sketch, okay? Let's see over here, I'm gonna put it over here. Let's say in the class called states, of course it's deferred. Okay, deferred class states. And there is a feature called execute. And then, for now, I'm just gonna sketch one of them. It's incomplete, but it will illustrate the idea. And then over here, let's say I always start with by displaying. Display, just that. So I'm talking about a state class, okay? Now, here comes a little bit more complicated, okay? Now, we know that there's only one single version of the execute that's defined in the state class. Now, let's talk about runtime. At the runtime, we know that at the moment, what's the dynamic type for S? Sit inquiry, agree? Okay, the dynamic type, I'll put in red. At this moment, S is simply of dynamic type sit inquiry, right, from here. So when I say S.execute, I know that I'm going to execute this only version of the execute. However, when I reach the first line of the execute here, it's going to call display. At the level of the state class, display is deferred, but that's okay, for compilation purpose, it's fine. But this version of the state will be inherited to, for example, sit inquiry class. Then, which version of the display will be called? Sit inquiry, yes. Let's do another example. And then, if I move on to this particular line over here, and we know that the dynamic type for this particular line, the dynamic type has been changed to something else, which is confirmation, right? So that's confirmation. Confirmation over here. And now, if I say S.execute, it's going to execute the same version of the execute feature that's in the state class. However, which version of the display it is going to call? It's confirmation, depending on what the context object is, right? Well, in this case, the context object S is of dynamic type confirmation. So the display over here will be called for confirmation instead. Okay, let me write it down. When we talk about 1, it's going to call the version of display from sit inquiry. When we talk about number 2 over here, it's going to call the version from confirmation. Okay, again, it's only a sketch. Okay, we'll see details. But if you can follow so far, that's good. That means you can think abstractly without seeing the code, which is an important technique to have. Any questions for me before I move on? Okay. So that's only about the design for state pattern. How many states should we have as a descending classes for state is completely up to your judgment. Okay, you may have 10 states, you may have 100, you may have 1,000, doesn't matter. Okay, depending on your application. Let's move on to the next one. So now I'm going to show you the code for the states. Let me use some little bit animation on the slide. So let's go step by step. We have a deferred class called state. I vaguely sketched that a little bit. So now let's see what exactly will be defined in the state class, which is deferred. Okay. First of all, we have a feature called read, simply deferred, which means the read feature over here is going to become implemented or effective in all the 6 descending classes, right? It's going to be 6 version of the read. Similarly, we're going to have 6 version of the answer. Oh, sorry. We also got answer. We also got choice. So these are simply the answer that we'll get from the user. And also we got display. We got correct. Also we got process. Also we got message. So far we only presented the defer features from the state class. So now let's see exactly what I meant by template pattern. Okay. Let's see this. Let's define the execute feature. First of all, we have a local variable here, simply called good. Good simply means if we have already got a good answer from the user. Until we actually got a good answer from the user, we're going to keep messaging them, let them know if something has gone wrong. And then we simply say display, and then read. Good is assigned to correct. Correct is going to validate their answer. And also, if it is not a good answer, message them, give them some message. And then eventually, once we go out of the loop, we're going to process. So now, hopefully now you get a more complete picture for the execute. Don't lose the big picture. If you go back here, these features over here are deferred. Only the execute feature is effective. That means at the runtime, there's only one single version for the execute, only one version. That's why it's called a template. However, depending on what the dynamic type for the current object is for the states, we're going to call the corresponding version due to dynamic binding of the feature, right? So now, for example, over here, let's see, that's why I put over here this part of the body of the execute here, I call it the template, which means it's only a single version of the template. It's not duplicated, which satisfies the single choice principle, right? So we don't have to repeat this template at every of the descending classes. But because of dynamic binding, I'll put it here. So now, for example, I will say display over here. I'll make some notes for you. Due to dynamic binding, the dynamic type of current objects determines which version of display will be called. Okay, so now that you can see basically dynamic binding over here correspond to the explicit if then else statements that we had to do in the second design, which is poor, right? So now let's see one more example over here. Over here we have S of static type states, and then at this point S is of dynamic type seed inquiry, right? As soon as we say S.execute, we're going to call this version of the template, right? There's only a single version. However, when we try to execute the body of this template over here, because S is basically of dynamic type seed inquiry, that means when we reach this step over here, display over here, it is going to call the version of display from the dynamic type seed inquiry. Is that okay? Anyone who's confused, I can draw some diagram to make it even clearer if you need it. Should I do that? Okay, maybe I should do that, just in case, right? Thinking this way. Now this is S over here, and as soon as we say creates, that means S is pointing to a seed inquiry object over here. And the seed inquiry object actually got its own defined version of the display, which is plus, right? That means it's effective. And also it has its own defined version of maybe correct and etc. Basically all the features that we have seen over here, they're going to be effective in the seed inquiry over here. Everything's going to be effective. So now, if I say S.execute, what it will do is, it's going to say S.execute is going to call this version of the execute. And then when we reach this step to execute the display, it's just going to execute this version over here of the display, just this version, specific to the seed inquiry. Now, what's going to happen if we go to the next line? If we go to the next line over here, let me use green. If we go to this line here, we're basically changing the dynamic type for S from seed inquiry to confirmation. S, rather than pointing to here, is now going to point to, over here, confirmation. Confirmation, which itself also is one of the descending classes over here that's effective, which means it will also redefine, for example, the display feature. That means over here, dynamically, it also has its own version of the display that's effective. Also, it also has its correct feature that's also effective. So now, when we try to execute S.execute, what's going to happen? Well, the version that's defined over here for execute, again, is going to be called. But when we reach this line over here for display, which version is it going to call? According to the dynamic type, right, for S, which is the confirmation. So that means this version of display will be called. Okay. Guys, are we okay for this? I hope that's clear. So we're basically talking about two design patterns over here. We talk about state pattern, part of it using something called template pattern. And it's really exploit the feature for dynamic binding and polymorphism of OO. Okay? Questions? Yeah.
Can you show the internal implementation of it? As to how they're
Display, we'll see that in just a moment. Yeah. You know what? I will give you some idea. How about this? Very simple implementation. Also, again, it depends, right? So now, how about this? Remember display, for example, according to your question, display over here at the state level is deferred. Nothing's there. And then let's say, for example, what we can do is, for the initial states, we may have to implement that. We can say display, do, and end. I can simply say print, for example, and then I would say welcome, for example. Welcome to this particular reservation system. Let's see another one. What about the help? Well, we also have to implement the display feature, but maybe accordingly, right? So now we also have to say display over here, and then do, and end, and then print. And over here, you can just do something here. For example, you say press on 1 to see this particular help option. Press on 2 to see another help option. Right? Is that clear to you? Yeah. Yeah.
No, I just needed to know that display was a different function.
Display is defer only at the state level. It cannot be defer anymore once you get to the descending classes level. Otherwise, those classes would have been defer as well. Right? Exactly. That's yeah. So now you can see that again. It's simply because we are using inheritance over here. So now we don't have to use if then else statements anymore. We don't have to say if dynamic type is current flight inquiry, then we do something for the display. We don't have to do that anymore. We let dynamic binding to deal with that for us.
Alright, so Professor, if you want to add a new class, a new state, you just like implement the state feature.
Very good question. Yeah. The question really is. So let's now talk about extension. It's a very good question. Let's think about the previous design. If we wanted to add a new states, we had to go to the display feature, add a new else if. We have to go to the correct feature, add a new else if, right? This violates the single choice principle. So now, if we want to add a new states over here, what does that mean? That means, let's say, for example, if I want to add a new states, I'll put it here. This is a new states over here, and it should be effective, right? Let me call that maybe pay, for example. It's a pay states. Now, since we declared this class to be effective, that means we have to, in this particular single class, like a single place, this single place, we have to implement all these features over here, right? Once we implement those, if the dynamic type happens to be pay, it's going to call the same version of execute, but all the feature that's being called will call the correct corresponding version that's defined in the pay, right? So it will work. It's a single place. We actually see this kind of extension also when we see the visitor pattern, which is a little bit more sophisticated, but we'll get there. Okay, guys, any question? Yes.
Is this state similar to the command in map 3?
It's not quite the same. It's a good question. We will talk about the command pattern a little bit later in the course. How about this? For now, just keep focus on understanding this. Once we get to the command pattern, I'll try to compare the two. They're not quite the same.
But it's due on 30.
But you know, for as far as the lab 3 is concerned, you don't have to worry about the command pattern. You just have to know where to modify the error message.
So it's okay just without?
That's okay for that. It's not nothing to do with this actually. Yeah. Well, I'm not trying to say using if then else is bad always, right? I'm just saying for that particular context, because that will violate the single choice principle. It's different. Okay. So now the next step is to look at. So now we're okay with the template pattern. Okay. So now what we want to do is, I think we did this already about the template pattern. So that's exactly what we said. Okay. So this is just the written form for what I just said in the iPad. Okay. Depending on what the dynamic type is, it's going to call the corresponding feature that's being used in the template. Okay. So hopefully that makes sense to you now. Okay, this, I'm going to show you exactly how to construct this diagram here. The only thing I want to mention is, remember when we talk about inheritance, we say something like a polymorphic array, right? That's exactly how the polymorphic array can be used in this scenario as well. The polymorphic array we had before, we have an array of students, and each slot can be either resident students or non-resident students. And over here at the runtime for the state pattern, we have an array of states. The static type is states. That means each element can be either initial, flight inquiry, seat inquiry, etc., right? Depending on which one you're talking about. We'll get to this runtime structure in just a moment. Okay, we'll get there. Okay, well, what I would like to do is I want to go over some code for application. Remember this diagram over here? I want to just, we don't lose the big picture. We talk about in the OO solution, we are going, what we just described, we talk about how you can put all the artifacts over here into a class called states. And we talk about them in detail already, about execute states specifically, the template pattern. The other part of the solution would be, we want to see how we can define this part over here in the application. So this is another module. So we got two modules in the state pattern. One is about the states. The other one is about the user of the state, the clients of the states. But let's see how we can do that, okay? And also, if you see the architectural diagram over there, you will see that over here, application, right? So that's the thing we're going to talk about right now, the clients of the states. Okay? So now let's see the code together, and then I will ask you some practice questions as well. So we're going to have a class called application, which has a constructor called make, and then we're going to have transition. So this is something that we reuse from solution number 2. So that's the good part about solution number 2, which is separation of concern. So we do have a transition function just with integer, the 2-dimensional array, okay? And then now this is something that we have seen already. Remember when we talked about polymorphic array before, we simply got an array of students. Now we have an array of states. How many possible dynamic types can there be for each element in the array? 6, right? Depending on how many states you have for the descending classes. Okay, good. Well, we'll see how we manipulate that in a test. And then we have the way we refer to the states. Remember, we got a polymorphic array, which I just mentioned over here. Polymorphic array. So we're going to only create 1, 2, 3, 4, 5, 6. We're only going to create 6 state objects at the runtime, only 6. And then the way we make a transition between the states is by seeing from which index to which index. For example, if I say I want to change from state number seed inquiry into confirmation states, for example, that means I'm changing from index 3 to index 5, for example. Okay, just referring to the state by the index. And specifically, the special case is the initial state is at index 1. Okay? Let's see how things can be understood over here. Okay, so here, initial states is going to be some integer. We set it to 1 in just a moment. And also the number of states, depending on what your application is, right? Depending on how your state transition diagram look like. If you have 100 states, you should set this to be 100. Okay? And also the number of choices, which means how many valid choices can you have for the transitions. Okay? And now this is constructor. You can see that to create an application, all we got to do is to pass how many states you want to have and how many choices you can have for the user. Okay? In our case, it's going to be 6 states, and also it can be choice number 1, 2, or 3, so 3 possible choices. And then you're pretty familiar with 2-dimensional array from lab number 1, so I need to go into too much detail. Now, can somebody tell me what invariant should be? If you haven't looked at the slides, you can think about it. I want to link between the 2-dimensional array and this notion of states or notion of transitions somehow. Let me give you a little bit of hints. Invariant should be some property that should really keep your class or objects consistent. So the critical feature we have is about this 2-dimensional array over here, the transition over here. Can the dimensions for this particular transition be arbitrary? No, it cannot be. How do you constrain the dimensions for this particular transition array? I agree. Okay, so now let's just talk about number of rows and number of columns, right? So the number of rows for this transition table should correspond to what? Are you sure? What? Number of states, right? Good. Okay, let me remind you about it. Well, if you want to adopt another convention, you can feel free. But for our discussion, remember, that's the transition table we have over here. Right? You can see the number of rows correspond to the number of states. the number of columns correspond to the number of choices we have, right? Let's adopt that convention there. If you want to swap the dimensions, feel free. Just want to use them consistently. That's fine. Okay. Okay. Let's now go back there. Over here. So now invariant should be, first of all, our transitions. The height, which would be number of rows, should be number of states. Transition that width would be the column size. That should be the number of choices. Okay. Are we good? Okay. So that's why we learn about design by contract. You always want to make sure the implementation is consistent with your abstract notion about states, transition table, etc. Okay. Questions?
Yes, Professor, so what if you have a state where it has more than 3 choices? Can this class still support it?
You can still support it. I see what you mean. Basically, what you're talking about is like this. Okay, let me just draw some diagram to show you. Okay, so now if you look at that over here, when I say the number of choices over here, I'm talking about basically like the valid value for the transitions, right? So now let me just draw some diagram over here just to give you some clarification. Let's say here. Let's say if I have 2 states over here, and then this, to go from here to here, I make transition number 1. From here to here, I make transition 0. Let's say 0 or 1. Let's talk about 2001 a little bit. Okay? So now over here, that's the starting states. And then I can go from state number A, state A to state B by using 1. I can go back by using 0. Okay? By the way, just to test your knowledge, is this a DFA or NFA? Can it be a DFA?
No.
Why?
The DFA requires every state we have all the
Exactly. Okay, it's just a little bit test of knowledge.
And the face is known by the fairy godmother.
Oh, you talk. Oh, I know that fairy godmother analogy. It's also using 3101 actually. Yeah, I know that. Yeah. Actually, I like that analogy. Yeah. I'm not sure about you, but anyway. Yeah, let's not mention his name here. But anyway, that's. Okay. Over here, you can see the possible inputs we can have is basically 0 and 1. These are the valid inputs. That doesn't really mean every state must support all the valid options over here. Okay? So that's a crucial difference, right? You can see from state A, we only support to go out by transition number 1. Okay? So NFA would be a more natural choice for your application, which means you don't have to support all the possible options for every state. Okay? So now in this case, that means that all the valid choices should be 0 and 1. So number of choices should be just 2, right? 0 and 1. Good. Now let's see the second part of the application. Now for application, second part, we still got a transition, we still got a states. I want to show you more features. How can we build up the transition table? Okay? How can we do that? Basically, you have to initialize it. We already initialized the 2-dimensional table to be of certain size. And now, how can we add transition to it? And how can we add state to it? Okay? Let's see how we can do it. We have a feature called put states. Basically, you just have to, over here. Now, one thing to ask you about. You can see for the put states feature over there, the feature argument there is of type states. That means, well, we learned very well, right, from the inheritance lecture. Dynamic, well, at the runtime, what object can you put inside the state array? Any descendant classes of the state, right? Okay, everything just link back to our inheritance lecture. That's why it was so important to cover. Okay, so now we know that this put state feature over here is like add students, right? Add students over here can add any kind of student, like we can add any kind of states. Okay, this is only a supplier code. We'll see exactly how the client code would look like. Okay, we just use the fourth feature of array. I'll let you go over details for the array. And then what about, we can choose some initial states. We can just choose whatever initial state should be. If you want it to be 1, just say choose initial 1. Okay? And put transition is interesting. Okay? I'll just show you the code quickly, and then we'll trace that in the test. Put transition, basically, you want to know which row, which column, and for that particular cell, what the entry value should be, right? Basically, you need these 3 pieces of information: target states, source states, and also the choice. We'll go to some example tests in just a moment. And don't forget, since we learned about design by contract, you should always put the appropriate preconditions and postconditions. Okay? Okay, about put transition, and then we just use the put. Okay, now let's see some example tests altogether. The reason I say non-interactive, I'm just trying to use some simple cases over here. And then eventually the application should really support a feature that is going to interact with the user, keep reading from them, and keep asking them for information. But for this example test, we don't do that, just for illustration. Okay, what I will do is I will switch to that particular test, and then let's do it together. Okay. So now there are 3 things we need in order to trace the code. Okay, let me just put you into the context. This guy here is the test. Okay, this guy here is our finite state machine, and this guy here is the runtime structure that we're trying to build. Okay, I just saved my time of drawing that from scratch, but we'll see exactly how we can build it. Let's go over line by line. Okay, first of all, we have the line over here. Let me use maybe yellow. So we have app of type application. And also the current states. Now you see that for this particular design, unlike the previous design, in the previous design, what's the type of current states? Integer. But now what's the type of current states? States. That's a crucial difference. We're using OO, that's why. Okay? And then we have some index over here. We'll see how the index is used in just a moment. First of all, we try to create app.make 63. The 6 over here is the number of states. Sorry. Is the number of states. And the 3 over here is the number of transitions. Okay, that's the first line. What it does is this part. It's going to create an application object over here, and then which got 2 attributes. It has got a transition table, which is a 2-dimensional array. And in our particular application, it's going to be 6 by 3. So that's why we got a 6 by 3 2-dimensional table over here, initialized to be all 0. And then we also got the states array, going to be polymorphic. Initially, they will simply just store nothing there initially, but we're going to add it in just a moment. Okay, so far so good? Okay. Now, let's see, first of all, how do we put the states? Basically, we want to initialize 6 different states of different types and add it in one by one into the states array so that it's polymorphic. One example could be over here. Let's see this highlight here. When I say app.putStates over here, what I'm trying to do over here is, you can see create initial.make and put it into index 1. So that means I'm creating this initial states object over here, and then I'm putting that into index 1 of the states array. Right? So you can imagine how the other 5 lines are going to continue, right? Just create different dynamic objects and put it into different indices of the array. Okay, so I just omit that part. Okay, so far so good? It's about how we create a polymorphic array. Those are the only state object we're going to create, nothing else. Okay? At the runtime, we're going to change dynamic type for current states when appropriate. We'll see. Okay, next line we're going to look at over here, app.choosEnitial. Okay, this one is actually quite a little bit trivial, a little bit subtle. Basically, we just want to say what the initial state is. The initial state is going to be the initial state is going to be the state object at index 1. So that means 1 over here, this is going to be the initial states. That's what we do. Okay, the next line. The next line here, app.putTransition. This might be the most complicated one to look at. Let's try to have a look. When I say app.putTransition, let's disambiguate about which parameter means what. If you look at maybe here, okay, remember the put transition is over here. This is the put transition feature that we talk about. It's going to take the targets, the source, and the choice. Okay, target, source, and the choice. Let's just see one example. So now we know that this is going to be the targets. The target, like the destination states. And 1 over here is going to be the origin states, the original states, the departing states, and this is going to be the choice. Okay? Let's see what this corresponds to abstractly to our diagram. It's actually quite easy. Can you see which one it is corresponding to? When we say target state is 6, 6 is over here. And we say that source state is 1, 1 is over here. And the choice is also 1. So we talk about this particular transition over here, right? So basically this put transition feature call is going to initialize exactly this part over here. Starting from this, make a transition call 1, and then end up with state number 6. Okay, that's exactly what you would do. How many more should we do? How many more? Give me a number. How many more transitions should we do? 7? 10. Good, very good. Okay, hopefully you can count, right? I hope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10. So don't be too surprised. We got exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 entries in the two-dimensional array. That's how we do it, right? Okay, now, one more thing to say. And over here, what about when we say the current states over here? We simply have an index over here. So we have the index which will keep track of where the current state is. You can see the current state over here is the of type states. And this index over here is basically index into the states array for reassigning the current state. Okay, let's see how we can do that. Initially, because we already chose the 1 to be initial states, that means app.initial will just be 1. So index is going to be 1. And then the current states over here, let's be careful. What's the static type for current states? What? State. Thank you. The static type is current states, states over here. I'll put in green. For current state, the static type is going to be just state, always the same. And what about app states index over here? Well, since we already chose the initial state to be 1, so that means the index over here will just be 1 to begin with. So that means the index over here will be 1. Now, question for you. After executing this line, what would be the dynamic type for current states? Can you do some lookup over here? That's how you trace the runtime. We know that index initially is simply just 1 because we already chose the initial state to be 1. So now index is 1, and when we do this particular assignments over here, okay, let's be careful. Let's do our normal practice as before. What's the static type for this particular expression over here? Static type. I heard states. How did you figure? Well, why don't you look at the states attributes over there? The states attributes for application, each element is of type states, static type. So now the question is, what's the dynamic type of current states? What do you mean the same? Just give me a name of the class. Initial? Good. First one, right? Because we know the index is 1. So that means when you try to do this particular assignments over here, you will go to index 1 into the array, and then try to go to initial, right? So that means it will be initial. Okay, after this line. And then what we will do is, we'll do some, just check to make sure it's really initial state, right? I'm doing something like an instance of over here. It's just a check to make sure it is really the case, okay? Now let's see how we can do transition, okay? The current state is initial. So this is the current states, okay? And now what we are doing is, we're trying to make some transition. I'll show you the line over here. Let me use pink. So now this line here is also very important over here. When we are trying to make a transition, remember the transition feature that we had before is simply an array of integer, right? You simply just return whatever transition the target state you're going to return, right? Let's have a look at this line here. So now when we try to do this particular transition, let's see what we have. Call the transition feature, and item is like a lookup, right? Just look up the, give the row number and give the column number. And now we say that index at the moment is 1. And then what about the column? Column is whatever choice that the user has entered, right? Let's say they have already entered 3, let's assume. So this is the current state, and 3 is the choice. Okay, this is the current states, like 1. How does that correspond to the table over there? That means we are now at current state 1, and then we are making the choice 3. Don't you agree? Are we okay so far? That means we got 1 here in the table from state number 1, and we are trying to make the choice number 3. What should be the what should be return value then? What should be the return value from this particular transition call? I give 1, and then I also give 3 as a column number, right? So that means I should return 2. And then, so that means this should return 2. And then so that means I'm updating the index to be the current states. So now I do one more assignment to do this properly. Oh, that may be a little bit unclear. What about yellow? If you look at this line here, transition itself only returns an integer, telling me which index to look into in the array. So now if I do this one here, and question for you, we know that this transition is going to return the value 2, which means index will be reassigned to 2. So now after this line over here, what will be the dynamic type of current states? What would that be? Huh? Speak out. Flight inquiry? Seat inquiry or flight inquiry? Well, which index? First of all, which index is that? 2, right? Well, we know that the return value is simply 2, right? That means index will be 2. That means over here, index that we're using here will be 2. At index 2, we have flight inquiry. Don't you agree? So that means it's going to be flight inquiry. And we do exactly the check that we did before to make sure it's an instance of flight inquiry. Are we okay for this? Okay. So now, one more thing to go over. I think we have a few minutes, right? 1 minute, 2 minutes, maybe? How about just 2 minutes? Then we are done. 3:48, 2 minutes. Good, thank you. Let's do 2 minutes. Oh, more than enough. Okay. That's the last bit. I will talk about the insight into state pattern on Tuesday to finish up the topic. But let's go over this. So the one we just did in the previous page is not interactive. We're just showing you how we can call the different features for the different classes, different objects. But now, this will be the last piece for the application class, which is called execute session. Again, we're going to have basically a from until loop. We're going to say an index is going to be initial states, the index that we talk about, right? Initial state, presumably just 1. Maybe just make it initial state over here. And then we're going to say the current states is going to be just index into the state array, like how we did it before. And then we're going to say whatever the current state is, we're going to execute it. We're going to say current state execute. And we also went over this part. Dynamic binding is going to make sure we call the right version of the different thing that's mentioned in the template for execute. And then finally, we simply update the index for the current states, and then make by calling the transition, right? Passing the index for the current states, and also what's the choice for the current states. Okay, guys, this is what I would suggest before next week. Before next Tuesday, look over this pattern very carefully. I'm going to give you, again, the insight into the state pattern. And then we'll move on to another pattern. It's going to be pattern after pattern for the rest of the course. So please stay on track. All right, I'll see you next week.